The floor is yours, ladies and gentlemen. What questions do you have for me? 84, 85, 10, 1. Question number 10. A light bulb has an average lifetime of 1,000 hours. So we want to use an exponential density function with a mean of 1,000. Okay, wait a minute. Exponential, that's that one that looks like this. There was a formula for that. Do you have that at your disposal? That's once I know what the f of x is. But even before I do that, what's the f of x equation specific to an exponential? We did an example in class about waiting in line, and then there was a discussion in the example in the book is about waiting for a phone call to be answered. There's the picture we're looking for on the page you've got open on the right there. So that should be somewhere around the area. Don, do you have it in front of you? What do you got?
It's c times exponential of negatives.
Okay, but then we had something else. We knew what c was in terms of our average. That was what we did as we worked it out, but a little further down, we talk about the average, we get to c is 1 over mu, where mu is our average. That's on page 577, just above example 4. So in our case, Jacob, the average was what for this one? So my function is 1 over 1,000 e to the negative 1 over 1,000 t, when t is bigger than or equal to 0, and 0 if t is less than 0. Yeah, they said right there, the average expected lifetime of the light bulb is 1,000 hours. So they gave it to me. So which part of the problem were you having issues with? Part A, part 1, or part B? Okay, so now that this is my function, I know that the probability of my light bulb having a lifetime between A and B hours is the integral from A to B of f of t dt. So in that first problem, the very first part, what's it tell me the lifetime of my light bulb is? Say again? Now that's the average lifetime. What is the probability that the light bulb lasts? Okay, so the first one says, what's the chance it fails within the first 200, right? So what that's asking is, what is the chance that my light bulb has a life between 0 and 200 hours? Which means I would need to do the integral of this thing from 0 to 200. But between 0 and 200, we use this version. So I can do this by computing I'm sorry?
Can you take 1,000 out?
You could.
Okay.
And part B says, what's the chance that my light bulb has a lifetime of more than 800, right? So that's from 800 to where? The average light bulb lasts 1,000. Some light bulbs could last longer, right? It's got to go off to infinity. So that question is actually asking, what's the chance that my x is bigger than 800? So that's the integral from 800 to infinity. Now, part B asks you to find the median, right? And the median is where I want this to have half of the bulbs have a life less than this, and half of the bulbs have a life bigger than this. So if half of the light bulbs whatever my median is, right? Then I want to find the number m so that the p of x being less than m is exactly a half. But this is an integral. And it's an integral like this one. So when you do that integral on the left-hand side, you'll get some expression with an m in it. And then you'll be able to use the 1/2 to figure out the value of m. And I don't know, maybe it's like 750. And that means that half of your bulbs fail before 750 hours, and half of them last a very long time. Since the average is 1,000, and there's a lot less in the picture, there's a lot less area over here. The average is going to be pulled way past the 50% line. So all three of these integrals give me the answers that I want. You see how they're connected, Jacob? Right. Now, we could just as easily have solved the integral from m to infinity, but if I have a choice between doing an integral with a 0 in it and an integral with an infinity in it, I'm going to pick the one with the 0. By the way, for your amusement, I believe the world's longest continuously burning light bulb is still operational. It's an Edison bulb that is in a fire station, and I believe it has been running for over 120 years at this point, without being turned off. Amazing. There's a webcam. Wish I was making this up. The internet's an amazing place. More questions? I even have bookmarks in all the right sections. But that means when somebody asks me a problem, you're going to have to read it to me. Yes, Jay. Say again? 8.4, number 8.
A purely competitive market, the price of a good is naturally driven to the value where the quantity demanded by consumers matches the quantity made by producers, and the market is said to be in equilibrium. These values are the coordinates of the point of intersection of the supply and demand curves. A, given the demand curve P equals 50 minus 120x, and the supply curve
120 or 1/20th?
1/20th x, and the supply curve equals P equals 20 plus 1/10 x. for a good, at what quantity and price is the market for the good?
Okay, best part. Those equations are straight lines. So my demand equation and my supply equation look like that. The supply has a positive slope, the demand has a negative slope. How do I find this point? Huh?
Can you just graph those that, like, on your calculator?
I absolutely could. I don't have my calculator. What do I do instead? Price on one has to be equal to the price on the other. I can set them equal and solve. Now, this is going to give me a quantity and a price. And those are the coordinates of that equilibrium quantity, is where the two cross. That'll be the x coordinate there. And the equilibrium price will be the y coordinate. I've called them Q and P respectively. So but that's only part one, because part two asks about producer surplus and consumer surplus, right?
So is this what they were talking about?
Yes.
Okay.
So my price is capital P. That's going to be the equilibrium price, the price I have at this point. Now I think I used Q0 for my quantity as the equilibrium quantity. But what this means is that everything that the suppliers put out, the market buys up. There's no people wanting to buy stuff that can't find it, and there's no leftovers sitting on the shelf. The market is in pure equilibrium, which rarely really happens. I don't know. Do I need B, Jack? Well, what's B say then? So those two surpluses, producer surplus and consumer surplus, should be areas in this picture. Go back and I look at the integrals. One of the integrals looks like that, and the other integral looks like this. Before I do anything else, I'm not even going to label which one is consumers, which one is producers. Let's look at the picture. Which of those two triangles that I made is the integral on the left? Okay, on the top one, this is an equation P of X, isn't it? And this is the number capital P.
No, I like the top as opposed to S. Like S being the hypothesis.
I'm still even more confused. Hang on a second.
Okay.
I have two triangles.
I was saying two and then S being the hypothesis.
But it's a hypotenuse for both of them. That's my problem.
Can P be the hypothesis? Line P?
Here's the right angle. That's the hypotenuse. Hypotenuse is always across in the right angle. So this one is number 2. And this one is number 1. In number 1, which equation are we using? The demand equation or the supply equation? Because that's the line D. Yes? And that's the people who are buying the stuff. Is that consumers or producers? What's that make the other one? And notice that this one goes with my supply curve, and that's where my producers come into the game. Now you need to do the integrals. And since you found capital P, you found Q0 in part A, you now know what to integrate. But they're triangles. You really don't need an integral to find their area, do you? You should be able to get the same answer both ways. And look, I drew the picture and I identified it. My picture is not to scale. Please draw a better picture than mine. Or at least label it better. Make sense? Wonderful. A lot of supply equations generated by gross revenue equations are usually cubic polynomials instead of straight lines, or they're exponential equations because we have that sort of diminishing die-off. There are still people who are willing to buy it even when the price is sky high, but there are very few of them. So in a lot of cases, having this sort of simplified version is less realistic, but still gets the point across. Because once I just get more complicated integrals, I just throw those in a computer and I'm done. This is why the business people don't do math. They just, hey, this is what it's supposed to be, go find that. They outsource to geeks like me. You had the same question. Did I answer your part as well? Wonderful. More questions. Yes, ma'am.
So 10.1 number 12 says, eliminate the parameter defined of
Cartesian.
Cartesian equation of the curve, and sketch the curve and indicate with an arrow the direction in which the curve is traced as the parameter increases of x equals 1/2 cosine of theta, y equals 2 sine of theta, from 0 is less than 30 of theta is less than 8. I just think I got confused on the Parmesan equation.
Oh, no, Cartesian just means X and Y equation.
Oh, seriously?
Yeah. Rene Descartes, the Cartesian plane. Nope, I want you to get rid of the theta and I want you to turn this into just an X and Y equation. But because I already see trig stuff, my preferred method for using this is going to involve a trig equation or a trig identity somehow, like the example we did in class. Now, you should probably best draw this on your calculator first so you know what it looks like in parametric. Now, since our calculators use t instead of theta for parametric, it's fine. Go ahead, just change the letter. So everywhere you see a theta, replace it with a t.
T itself is just an indication of directionality. Am I confused in actual thought? Like X is this, Y is this, what is T?
Oh, so t is the most common way I tend to think of t is time. We start the clock. And all of a sudden, tick, 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 I draw the curve, right?
But it is sort of like a vector-like idea because it's giving you the direction.
There is a vector idea involved here as well, yes. What you could say is that t is a pointer, pointing to a spot on the curve, and as we change t, we point at different spots on the curve. Chapter 12 addresses this idea in more depth, and most of what we do in Calc 3 is called vector calculus because it uses that idea as the basis for doing more stuff. And there's another weird line for you as well, because that's why in White and Nerdy he says, I do vector calculus just for fun. Because it's Calc 3. So yes, but now if I graph I do have my calculator. I lied to you earlier, Dom. I do have it. If I take my calculator, I can graph this in parametric mode, and I can see what it looks like. Mode, yes, I'm still in parametrics. So 1/2 is 0.5 cosine t, 2 sine t, window. I only want to go from 0 to pi, so I will change my p-values to accommodate that. And then I'll just leave the graph where it is and see if I see a decent picture, and if not, I'll change my window as well. Graph. Oh. Notice that it has an orientation. Where did we start? So you know it's going, draw an arrow on the graph to say, hey, we're going this way. What does that graph look like? Let's change the t values for just a moment. Instead of going to pi, I'm going to go to 2 pi. Since I have trig functions, I normally think of trig functions with 0 and 2 pi involved. I know that shape. What shape is that? Which means I should get the equation for an ellipse. And conic sections, there's a handout on our Canvas page full of conic sections that we will go over again next week after break, because we're going to do conic sections from a new perspective. At which point I will bring my conic sections toy with me. But this appears to only be half of that, since we're only going to pi. And that's what the parameter allows me to determine, is what part of this graph I get. When you eliminate the parameter and result in the Cartesian equation, then you only have x's and y's, and you would say, oh, your graph is part of this thing. Better? More questions? So what does it say?
Show that the parametric equations x equals x1 plus 1 x2 minus x1 and y equals y1 plus 1 y2 minus y1 times t, where 0 is less than or equal to t, that's less than or equal to 1. Otherwise, that shows p1 of x1 y1.
Sure, it does. All right, wait a minute. I claim that those parametric equations give me the line that joins these 2 points, right? So, ignore the parametric part for a moment. You have these 2 points. What's the equation for the line between them? So this is an algebra drill that I need you to remember. Yes, that is the slope, but that's not the whole line. How do I get the rest of the line? There are at least 2 different ways to do this next part. That's a really long way to do it. And then I can figure out what b is, right? I can take y equals mx plus b, and then I can solve for b. Or I can use the point slope version, y minus y1 equals mx minus x1, and I can multiply all that crap out, right? Then I claim this set of parametric equations matches this Cartesian equation. I can eliminate my parameter. If you do elimination of parameter up here, so let's take our x, solve that for t. Then take that t and put it in here and multiply all this out, you'll get this equation. And then you would say, oh, look, it is the same line. And when t is 0, we're at x1, y1. And when t is 1, x1 plus x2 minus x1, we're at x2, y2. So we only go from point 1 to point 2. We're always in between there. I'm going to steal your idea again. Another way to think of this is to think of vectors. You have 2 points. To get the vector that goes from one to the other, you take the head minus the tail, right? From point 1 to point 2, I take head minus tail. Head minus tail. So this is saying start at the point x1, y1 and go that way. And we always start between 0 and 1. We just stretch that vector out until it fills up the whole space between point 1 and point 2. The physicist in me is jumping for joy at that image. The diffusion mechanics across the semipermeable membrane work exactly this way. It's biochemistry. Better, Tom? Yeah. Then in part B, they give you numbers, right? They just say, here, do it. Here's some numbers. And then you can check and see that it actually does what you want it to do. I do know that our calculator only graphs either in parametric mode or in Cartesian mode. It doesn't do both at the same time. In your Mac, there is a built-in grapher program that can do both at the same time. Under Utilities or Other, there's this grapher program here. And if you launch that, you can graph implicit equations, explicit equations, parametric equations, even other kinds of equations, all one on top of the other. So you could graph the line in y and x and graph the parametric and compare the two. I like it so much, I pinned it to my taskbar. It's there all the time. Plus, you could do the same thing in Desmos. You could do the same thing in Wolfram Alpha, or you could do the same thing in one of the free quick grapher apps. More questions? Tomorrow, we do calculus on it all.
Can you just clarify that for 20%, describe the motion of the particle's position x, y, as t varies in the given interval. And the question is x equals 2 plus sine t, y equals 1 plus 3 cosine t, from pi over 2 to t to 2 pi.
What you're doing?
Asking you is where the particle is moving during that interval, like which direction.
draw me a curve and say, we started here, we ended here, we went this way. That's it. Really, you can just draw the picture.
Okay.
If you really wanted to, you could then take that picture and eliminate the parameter and tell me what, I said if you wanted to. More questions? So read me the equations again. Y. And it's pi over 2 to. Okay. So literally all I'm going to do is I'm going to take those equations, put them on my calculator. And then I'm going to change my T window to match the numbers. Pi over 2 to 2 pi. Now, I know because this number, cosine could be as big as 1 and as small as -1, these y values are going to get as big as 4. So I know that I need bigger y ranges because I'm only going up to 2.5. I need to go up at least to 4. So let's change all these numbers by adding 2. Move my graph up a bit. X goes as big as 3, so I think I'm still good there. Graph. Oh, apparently didn't go low enough because there's some of the graph down at the bottom that I'm missing. So let me make this bigger. Where did we start? Where did we end? What direction did we go? Copy this picture over and you're done. So yesterday evening, once I'd gotten home and had dinner and done what paperwork I needed to do last night, I did spend a bit of time on the internet. And one of the things I found was a video about, I gotta turn the light out, too much light out, about the orbit of the moon. And this video describes the orbit of the moon, not around the Earth, around the sun, as a parametric curve. And it turns out that the orbit of the moon is not actually a circle. And it's best described as a parametric curve. And I saw that by Minute Physics, and it's on YouTube. But I also saw on Instagram a short about families of parametric curves, our list issue figures. It came up in a different spot. So I threw both of those links onto the Discord channel associated with this course. The Discord link is on our syllabus. More questions? The following is my 1-minute pitch on why you should take Calc 3. Take your parametric equation. Add z. We already know what that shape is, right? What shape is that? Yeah, a circle of radius 1. Ready? Now what happens as you go around that circle? Not quite. Because we're still describing the motion of just one dot. Our dot went in a circle. Here's X, here's Y. Point it out right at you. Put your right hand out in front of you. 4 fingers X, your second finger is Y. Z. As I go around the circle, I go up. Z keeps getting bigger as t goes from 0 to 2 pi. What shape am I describing now? A helix. I'll take 2 of them, offset them. All of the stuff I want to do with physics in 2 dimensions. All of the stuff I want to do with calculus in 2 dimensions. The stuff we're going to do tomorrow. I can now do it 3D if I think parametrically. Real world physics. The reason calculus in the 1600s and 1700s was so popular was because it applied to physics. Real, modern day physics is done parametrically. When you think about motion, we're looking at how these 3 dimensions move with you. My favorite version of this is Roller Coaster Tycoon. You ever played that stupid game? How do you know if the roller coaster is going to kill people? No, before you test it, you don't want to kill people by testing it, do you? They run a simulation and they measure the force in all 3 dimensions on the person in the seat. I lived in Florida for 18 years. There used to be a science class at Disney where they gave you vests with accelerometers in them. And you rode the roller coasters and mapped out the forces on the roller coasters. Anyone used to do it too. Now you do it with your phone. Literally, you strap your phone on a harness to the center of your chest. It will measure the acceleration on you at any given moment. Because those accelerometers are built into your phone. That's how I figure out that my roller coaster is not going to kill people. It doesn't throw me out of the seat when I go over the bump. It doesn't slam me in the side hard enough. Because I measure the force vectors in 3 dimensions. I do calculus. And that's what we start with. That's where we start next semester. Please take this course. It is so useful. Anyhow, thus endeth my pitch. Everything becomes parametric equations. More questions on this stuff? How to put it into... Okay, so what you need to do is you need to take these 2 equations up here and show that they match this one down here. So that's where we do our elimination of parameter up here and show that this equation turns into this one with this slope in here. Then you're saying, hey, look, these parametric equations match the equation for the line I want. And if I can describe a line as a parametric equation, then I can describe any curve as a parametric equation, whether it's in 2D or 3D. Let's then move on to next semester. Give me the paper without tearing it. At this point, we have two choices. I have 10 more minutes of your time, but if you're just going to stare at me, I can let you go and just pick this up tomorrow. Or somebody can ask me another question. 14? Which one? Somebody needs to read me 14 because I don't know it. Okay, wait a minute. Negative 2t. Okay. What's a negative do in the power? Okay. My goal is to eliminate the parameter, right? Because it wants to, well, you can draw this as is, yes? Graph it just by putting it in the calculator. But it does say eliminate the parameter and give a Cartesian equation. So I need to get rid of the t's and just write this in y's and x's. That's nasty looking. What can I do with this expression to make it look like e to the t instead of e to the 2t? The exponent is two things, right? It's the 2 and the t. When you're multiplying exponents, how could you rewrite that? I'm multiplying in my power, same as doing what other operation with powers? Aha! Let's put that here. I see an equation with no t's in it. Do you? Suddenly there are no more t's. I've eliminated my parameter. Then I could actually check it by graphing it in x and y and by graphing it parametric and seeing that they both give me the same shape. By the way, that's not the only way to do this. Instead of looking at the multiplication of powers, you could say, oh, how do I get rid of this and write a t in terms of x? How do I get rid of an e? With an ln. And then I could take that and put it in here. But then if I do a bunch of simplifying algebraically, it's the same thing. Properties of logarithms come into play in that case. Better? I don't know what 12 is.
X equals 1/2 cosine theta, y equals 2 sine theta from 0 to
I was about to say, I've heard these numbers before. Yes, right there. We drew a picture. Right? It's okay. What that means is you have to go back and watch the video. So which one do you want to check? Number 6 in 8.5. Start me off. What's the problem itself? Oh, right. We have to show that that's a probability distribution function first. So for this to be a probability distribution function, I need two things. By the way, that's not the only piece of that, right? Isn't there some restriction on the x values? Aha, and it's 0 everywhere else, right? There, 0 otherwise. So I need to make sure that that's always positive. Let's start with the easy part. Graph this without the k. Three x minus x squared looks like part of a parabola, right? So it's going to look like that. But now I need this to be true. So you'll need to do this integral. But since my function comes in 3 pieces, my integral can come in 3 pieces. The piece that is to the left, where x is smaller than 0, the piece between 0 and 3, and the piece to the right, where x is bigger than 3. What do you know about this integral? But I know more. What's the function on that side? That's only here between 0 and 3. When I'm bigger than 3, what's the value of the function here? What about here? So those two numbers are gone. Because our functions have finite support, yes. But you'll notice that the function with the exponential, we could have gone from m to infinity, and then we would have had the infinity in there, right? So I've cheated and I've made my functions work out nice. Yes. I'll save the ones that don't work out nice for prop and stats 1 and 2. Now, when you do that middle integral, you've got a k floating around in the middle of the problem, right? So as you do this, you're going to get some expression with k. But you want that to be equal to 1, don't you? So you set it equal to 1 and you solve for k. Then your function is probability distribution. Now you found the value k that makes it work. That's part A, right?
Yeah. Oh, that's part B is
Which means you do the integral from 1 up. Now that you have the k value, you know what the answer is. I don't know what that expression is going to be, but it's going to be something in k equals 1. Better? Right. Ladies and gentlemen, we have reached the end of the class period. I will see you all tomorrow bright and early. If you have more questions, come down to the Enrichment Center. That's what I'll be for the next 90 minutes.